Hi. Section 3.2, the derivative as a function. In section 3.1, we define the derivative at particular point, x0, f of x0. Now in this section, we'll define the derivative as a function. Okay, let's see this note. Because a derivative can be considered as the slope of the tangent line or as the rate of change, we may sketch the graph of derivative using the graph of fx. Let's see this example. Here, graph of f is given, and we'll use it to sketch the graph of derivative. Now, once you choose this point, that one, if this is x0, then at the point, the derivative will be 0. Let's try to use red pen so that derivative will be 0 at point. If x0 is this point, again, derivative will be 0. Again here, because here now tangent line has a slope 0. Okay, now we can divide the region into a few of sub-regions like that. Then, in this region, if we are choosing any point here, then now the slope is negative. For each point, once you are choosing x here, then slope must be negative, and so on. But it's approaching, x is moving from, so that it reaches over there, then now the slope must be 0, which means that here is negative and increasing to become 0, like that. Once your x0 or x is between here, then now that is 0, and slope is increasing, and now becomes 0, so that slope is increasing and becomes 0. And in this region, the slope is decreasing and becomes 0. Slope is decreasing and becomes 0. And here, although this region is increasing in f prime, yet this is negative, which means that original graph is going down. Now, in this region, now the slope is increasing from 0 to becoming larger and larger and larger, so that it is increasing like that. So that is rough graph y equal f prime of x for the derivative. Okay, here we have a strategy for graphing the derivative. See where the rate of change of f is positive, negative, or 0. We did it and when we are solving the problem. Now, we try to estimate roughly the size of the growth rate at any point x. Also, we try to do. And also see where the rate of change itself is increasing or decreasing, and these two are quite similar. But if we want to get quite detail of the sketch, then we have to consider this one quite accurately. But anyway, this is a rough graph, rough sketch of the graph of the derivative. Let's do one more time. F is given. Now we'll use it to sketch the graph of the derivative. Again, okay, at this point, the slope must be 0, which means that derivative is 0. Again here, the slope must be 0. Again here, the slope must be 0. Again here, slope must be 0. And looks like at the end here, slope must be 0. Okay, so we can separate out the regions in this way. Okay, here, and we have this one, and here we have now. Okay, for each sub-region, this increasing, which means the slope is positive, so the slope is positive and becoming 0. Okay, so given in this way. And in this sub-region, now slope is negative, slope is 0, now negatively larger, and again becoming 0. So it is negatively larger and becoming 0. And this region is slope is larger, 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 and here yet slope is positive, but slope is becoming smaller to become 0 at the point. So that this is increasing and go down 0 when you are considering y equal f prime of x, right? The same way for that, okay, this region is the same as that, so that again is going down and becomes 0, and this region is the same as that region, so that is increasing and go down 0. So that is the graph of y equal f prime. And in the previous section, we have focused on finding derivative at a particular point, and that is the same as the slope of the tangent line. Now in this section, we'll try to define derivative as a function, and now by considering the limit at each point x in the domain of f. So that is definition. Derivative of a function fx with respect to x is the function f prime, that is now derivative function, and the value is the limit. If the limit exists, then now that is becomes the f prime x. Okay, rather than x0, particular point, rather than x0, we are using now the arbitrary point x in the domain of f. So only the difference is now x0 is replaced by x. And also here in notation, rather than f prime x0, we are using f prime x. Once you try to find the derivative, then maybe at some point the limit doesn't exist. So that here domain of f prime may be either the same or smaller than the domain of f. It's a natural consequence, right? Okay, let's try to find the derivative of f using the definition of derivative. Okay, here. Now, the definition is that first we have to manipulate the difference quotient f x plus h minus f x divided by h, and then later we'll try to apply limit as h approaches 0. Okay, we'll manipulate this one. X plus h. So rather than x, we put x plus h. So it's 4 minus 8 x plus h minus 5 times x plus h squared. That is f x plus h. Now f x is the same as 4 minus 8x and minus 5x squared. Right? Okay, divided by h. Okay, we'll expand here so that is same as now 4 minus 8x here minus 8h minus 5. Okay, we'll put it everything inside parentheses, and x squared plus 2xh plus h squared. Okay, minus, now 4 minus 8x minus 5x squared. Okay, divided by h. This 4 and 4 will be cancelled out, and minus 8x and minus 5x squared minus 5x squared. So remaining parts are here minus 8h, and now along with minus 5, that is 2xh plus h squared divided by h. So that once h is cancelled out, then there is minus 8 and minus 5, and that is 2x plus h. So here, once limit is applied from here, let's try to apply limit h approaches 0 and the quotient, and f of x plus h minus f of x divided by h, which is the same as now minus a minus 5 and 2x plus h. Okay, once h is approaching 0, then this will disappear, and we can get minus 8 minus 5 and 2x, or we can write minus 8 minus 10x. Okay, so that is the final answer. Here, okay, we'll try to see part by part. For the constant, here we appear here and appear here and cancel out. So later on, nothing is contributed from this term. Now, how about here minus 8x? It appears here, and that term is making here now this portion, and here, okay, it's not easy to see. Okay, I'll use this one here, and cancel out, and remaining part is that one, and then eventually 8h and divide by h, so that is made. Now, how about that term? Okay, this term appearing here, and cancel out, and then remaining part is that one here, this portion, and eventually we have that. So when you are working on this difference quotient, then you may use part by part. That is, you can rearrange this one. So contribution from this term and contribution from that term and contributions from the last term, you can separate out, and later on you can combine them. So here, for this one, there's no contribution. And probably if you learn AP calculus from high school, then derivative of a constant term is 0, so no contribution. And from this one, we have a minus a. From this one, we have eventually minus 10x. Okay? Okay, let's see this example. Fx equals square root of x, and we want to use the definition of derivative to find f prime. Okay, here, now limit h approaches 0, and f x plus h minus f of x divided by h. That is definition. Now, that's same as same limit. Fx plus h is square root of x plus h, and fx is the same as square root of x divided by h. As h approaches 0, top and bottom are simultaneously approaching 0. So to get value, we have to work on rationalization so that conjugate can be multiplied. Then after multiplication, it will become x plus h minus x divided by h, and conjugate, which is square root of x plus h plus square root of x. Now this x and minus x cancel out, h cancel out, so that will be same as here 1 over square root of x plus h plus square root of x. And once h approaches 0, then we can get here 1 over 2 square root of x. So that is the derivative of the given function. Now, we have to say domain of f prime. Okay, so that is, we can say this is f prime of x. Of course, for f itself, the domain is now x is larger than or equal to 0. But here, for that function, apparently once x is 0, then value doesn't exist, so that for that one, here the domain is now x positive. So this domain is smaller than the domain of f. Okay, now we'll find the tangent line to the curve at 4. For that, we have to find the slope. And we know that the point is x equal 4, then y, square root of 4 is 2, is passing this point. Now we have to find the slope. So we can use a point slope formula to find the slope. Now by using definition, we can get the derivative at the point, which is same as limit h approaches 0, f of 4 plus h minus f of 4 divided by h. Okay, if we consider the quotient, then that is the square root of 4 plus h minus square root of 4 is 2 divided by h. Once h is approaching 0, then now top and bottom approach 0 together. So we need rationalization. So that's same as a limit. Here square minus square. So the 4 plus h minus 4. 2 squared is 4 divided by h times its conjugate, which is square root of 4 plus 8 plus 2. 4 and minus 4 will be cancelled out, and h cancel out, so that we have here now limit 1 over square root of 4 plus h plus 2. Once h becomes 0, approaching 0, then now that square root of 4, which is 2, so 1 over 2 plus 2 is 4. Okay, so slope is 1 over 4. And so we can get the tangent line, and we already know the point. So here y minus y0 is 2, and equal slope times x minus x0, which is 4. So that is the tangent line. You can simplify if you want. Now, in this computation, we may consider this one here. That is basically a definition of f prime at 4, x0 equal 4. Now, this can be obtained from this one. And already for arbitrary point x, we found here f prime. So from here, once x equals 4, then f prime at 4 equals same as 1 over 2 square root of 4, which is now 2 so that and is 1/4. So we can get the same result for the derivative at the point 4. Now the derivative are notated various way, and we'll use usually f prime or y prime, but we'll try to use also occasionally df over dx or dy over dx, and sometimes fx side of d over dx. So we'll use these notations this occasionally, but very frequently we are using these 2 notations. And some people are using this notation df or d sub x of f. And each notation is its own benefit, so that in some situation, some notation is much more convenient than the others. Anyway, here we'll use this and that most frequently, and occasionally we'll use these notations. Okay, this is part A, part 1 of section 3.2. Thank you.